today will be about optimization. And the originality of today's lecture is strictly zero. So we will look at the Karush-Kuntaka conditions and at properties of dual optimization. And this is essentially the chapter 5 in the fine book of Boyd and Vandenberge. That's Cambridge University Press in 2004. And the second part of today will be about linear programs, and I will give examples why these are important, and the simplex algorithm, a means to solve linear programs, and that will be based on a short course that Vandenberge gave in Denmark in 2010. So, as I said, originality zero, but I hope that you do find it a useful summary. And we have looked at some pattern recognition methods where optimization plays almost no role, like decision trees. So they are greedy, and you don't need any fancy optimization strategies. But then we looked at support vector machines notably, and all the more advanced methods, so that build on variants of the support vector machine, or the most recent research that we will also discuss next week. So how to make structured predictions. All of this involves optimization to various degrees, and this is why we're discussing it today. I will start with Lagrangian. First, we have the following optimization problem. We want to minimize f0 of x. So this is our objective function, subject to a couple of constraints. Which I will abbreviate, subject to, I will abbreviate by ST in the following. Subject to the following constraints. We have inequality constraints. We want the functions fi of x to be no larger than 0. And we have a total of m inequality constraints, let's say. And then we also have a couple of equality constraints, so functions hi of x that should be 0. And we have a total of p of them. Now the Lagrangian introduces the dual variables or Lagrange multipliers. Lambda and nu for the inequality and equality constraints. And so these are multiple dual variables, or it's a vector of dual variables. This one is associated with the inequality constraints, that one is associated with the equality constraints. So those are the dual variables or the Lagrange multipliers. Okay, and we now incorporate these constraints into the objective function by adding here sum of lambda I times fi of x and sum over nu I hi of x. And so we have the primal and the dual variables, and we can build the Lagrange dual or just dual function. Which is no longer dependent on the primal variable, and the primal variable is minimized over. So I'm using here the infimum over x element the domain, which I will specify in a moment. So the domain set D is given by the intersection of the domain of my original objective function with the domains of my inequality constraints well, I should write an intersection with the intersection of all of those and the intersection with the domains of all the equality constraints. So note that domain is different from the feasible set. So this is just wherever these functions are defined, where they take values larger than minus infinity. Okay, so I gave a handout, at least to those who were here last week. And again, this picture here is taken from the book of Boyd and Vandenberger. This is the first picture in figure 5. And it has, well, lots of content, so we can stare at this for a while. So first, the continuous line here is the objective function f0. And in this case, we only have an inequality constraint. So we have an inequality constraint function f1, which is shown dashed here. And we're now looking for the minimum of this objective function f0. So we're looking for the minimum on this solid black curve in those areas where f1 is smaller than 0. So you see the 0 horizontal line here. This is the feasible set. So this is where f1 indeed takes values smaller than 0. And if we're now looking for the smallest value in this domain here on the black curve, well, you can tell by eye, it's going to be that. But obviously in higher dimensions, this becomes harder to visualize, and this is why, you know, there's a point in doing all this math. Now, we built the Lagrangian by taking the original objective function plus lambda times this constraint function. We have no equality constraints, we only have this inequality constraint. And this gives you a family of curves, some members of which are shown here. So the black curve was just the objective function, and the first dashed line was the objective function plus lambda, which was set to 0.1 times your constraint function. And the next curve is for 0.2, 0.3, and so on. The final curve here is for lambda set to 1. So we have the objective function plus 1 times the constraint function. And, well, this gives us, if we now minimize for a given value of lambda, if we now minimize over these Lagrangians, we get out the dual function. And we can do that. So let's say we're starting at lambda equals 0. Then our optimum across the entire domain, our minimum, will be here. Okay, this is now, if we forget about feasibility, if we're looking for the smallest value anywhere in the black curve, this is going to be it. And this is going to be my dual function evaluated at lambda equals 0. You see here an inset. On the horizontal axis is lambda, and on the vertical axis is your dual function g of lambda. So the first dot that I'm pointing to here is this one there. Now we're moving to lambda equals 0.1, which gives me the first dashed line here. And we are again looking for the global optimum, which will be round about here. So just very little bit larger than the original one. So I go to lambda equals 0.1 and I plot this value. Okay, and I keep doing that until something dramatic happens, namely my minimum, if I go to larger values of lambda, is no longer located here, but my minimum now jumps location-wise over there. Okay, so for lambda equals, what is this, 0.6 or so, the minimum is no longer here, but the minimum is located there. And for larger values of lambda, this part of the curve of the Lagrangian becomes lower than that part. Well, and these points here correspond to the right flank in this picture. And where something dramatic happened, where our minimum jumped in space, this corresponds to the point where we have a kink over here. Okay, so if we don't do this for just 9 different values or 10 different values of lambda, but if we do this continuously for all values of lambda, we can trace out this curve here. This is the dual function. And the dashed line, by the way, here shows you the optimum of our original problem. So that was 1.5 something. And well, this picture has a lot of information, because note that the original function, the objective function here, was not convex. It was, it even had 2 local minima, one here and one there. And nevertheless, in the dual domain here, we get out a function that is concave. So a concave function is easier to optimize over. And we will see in a moment that that's a general property. In fact, no matter what the primal problem looks like, the dual is always going to be concave. Now, that sounds almost too good to be true, because a purely convex or purely concave problem is much easier than an unconstrained one. Surely there is a price we have to pay. And, well, the price that we have to pay is that if we now look for the highest value of this dual function, it's going to be here. This is not going to be quite the same as the optimum of the original function. So we will see in the course of the first hour or so of today that the dual function is a lower bound for the primal problem, and there are settings in which the dual function actually reaches the same answer or the same optimum value as the primal problem. But there are other cases, like the one shown here, where there is a gap. This is the duality gap. And what this means is that by going to the dual domain, we solve a much simpler problem. However, this simple problem is only an approximation to the original one. So we can solve this dual problem oftentimes exactly or very conveniently, but unfortunately it's not quite the problem that we wanted to solve. It is just an approximation in general. In some cases, as I said, the duality gap is 0, and then the answer is going to be exact. And in those cases, the advanced algorithms, they play by using both the primal and the dual domain and somehow narrowing in from both sides. So let's see why, in fact, the dual is always concave, yes?
Why is it important to only look at the numbers
Larger than where lambda is non-negative, you mean? Yeah. Because this property of the dual being a lower bound and so on only holds for strictly non-negative, or only holds for non-negative lambdas. So, on the next slide, you will see that to get this bound property, we must have a lambda larger than or equal to 0. Only then can we guarantee.
And why is the feasible set only in the area where constraints larger is smaller than
So this is the difference between domain and feasible set. So on the problem that you saw, the domain was the entire real line, so from minus infinity to plus infinity, but the feasible set is only where the constraints are fulfilled. and we had this side constraint, this inequality constraint, that f1 should be smaller than 0, smaller than or equal to 0. Can you go back to the screen, please? And then the feasible set is only where this property is true. And well, this is the formalism, and if your constraint looks slightly different, let's say in your original problem formulation, let's say you want to solve some kind of manufacturing optimization problem or a stability problem or so, let's say if your constraint is originally an inequality that wants to be larger than 0, rather than less than or equal, then you will try and multiply it with -1 in order to bring it into the standard form. So I think that all typical constraints you can express in this form. Yeah? That's you. So that the derivative should be, what do you mean by differentiable? That the derivative should be larger than, smaller than, or something like that? Give me an example. Yeah. Yeah. Well, but the specific example that you gave, so I... Mm-hmm. Mm-hmm. So yeah, let's discuss it later. I think you can always bring them into this form. Okay, let's see if we find a counterexample. Okay. So L itself, this is a function which is affine in the variables lambda and mu for a given x. So an affine function is one, so for example here we have a plane plus an offset, which is an example of an affine function. And affine functions are both convex and concave at the same time. So I can say that for a given x, I consider this to be a concave function, which is true. It would also be convex, but for now I'm interested in the concavity of this Lagrangian here. So it is concave, and by the way also convex, but I don't care now, in lambda and nu for a given x. And to go to the dual, we now have this infimum operation. And the infimum, if we have the infimum of a sum of several terms, the infimum preserves the concavity. So an easy way to see this would be if we have, let's say, a concave function here and another concave function, then the infimum is going to be at each location the lower of those. So the infimum of these two curves is going to be this one here. And this is still concave. In fact, it's more concave than the original terms. So this is what I mean when I say that the infimum, the inf operator, preserves concavity. And what we have then is that the dual function overall is concave. In fact, it's always concave, even if the primal is not convex. The original problem here. So that would be the primal problem. And the dual problem will be to maximize over those dual variables. Oh, so again, what is convexity? I will just show it in terms of pictures. Convexity is so important, and thanks for asking. It's so important because in optimization, it is this property that determines if a problem is hard or not. We were looking at convexity when we were talking about the hinge loss and support vector machines and so on. So let me show you a function. So let's say a parabola, or here a set of straight lines. Those would be convex. And let me here show you an example. This function still has a unique minimum, but it's no longer convex, because if I connect one part of this curve with another part, there are some regions where I'm cutting the curve itself. So here, you see I have intersected my original curve. This is why it's not convex. And if you look at robust potentials and so on, then for the same reason, these are not convex, because again, if I intersect, if I connect any point with any other point here, then I intersect my original curve, and this is thus non-convex. No, convexity, so first of all, convexity has nothing to do per se with Lagrangian. But if we talk about the optimization, then it being convex would mean that both the objective function has to be convex and the constraint functions would also have to be convex. Yes. This is the extreme case, so a straight line, because if I let's say I connect this point with that point, just like as I connected this one with that one, or let's say this one with that one here, there's no area that I could shade in red. This is why it's convex and concave. Yeah, so affine functions are the only ones that are both convex and concave.
I think the mathematical definition of convexity and concavity is just by the second derivative. So if you change the sign of the second derivative, then you will have a function that is either convex or concave, depending
Yeah, so you're right. If the second derivative exists, then convexity would mean that it has to be I'm not sure now if it has to be strictly larger, or I think it can be larger than or equal to 0 and still be concave. But you see the advantage of those set definitions or about the intersections is that this one also works for functions where the derivative does not exist everywhere. Okay, and well, in optimization, convexity is the boundary between paradise and hell, essentially. Okay. So we got out the property that the dual is always concave, and we're going to try and optimize the dual. But the price for the simplification was that we only solve an approximation this time. So the dual lower bounds the optimal value P star of the primal problem for positive lambda or for non-negative lambda. We have no constraint on nu, so nu could be larger than 0 or smaller than 0, or it could equal 0. So to see that, we take an arbitrary but feasible point x tilde. Feasible here means that the inequality constraints are fulfilled and the equality constraints are fulfilled. And then for lambda non-negative only, we can write our Lagrangian for this feasible primal variable. I'm just using the definition now. Okay. And we had just said that being feasible, that this first term here was less than or equal to 0, and I required that lambda was larger than or equal to 0. So overall, we get a contribution that is either negative or 0. And this one here is also 0, because we required that this be feasible. And so if you look at this overall, we get something that's either 0 or negative. And this is why all of the above is less than or equal the original objective function value of this feasible point. Okay, now we want the dual. So we look for the minimum over the domain. And this is now, this infimum here is one that goes over the entire domain. So that this is more than just the feasible set. So entire domain, whether feasible or not. And if we compare this to just the feasible part, then we must have an inequality here. Because it being feasible means that we have imposed additional restrictions. And if I relax them, I should be able to find lower or lowest values that are at least as low as within my restricted region. And then from the line above, we saw that this is less than or equal to f0 of x tilde. Okay, and so if we look at the left and right hand side, the dual being less than or equal the objective, this holds for any feasible point. Including its optimum. And this is why we find that overall our dual function is a lower bound to our primal optimal value. So P star was the optimal value of the primal problem. And this inequality always holds. But it's meaningless if our dual becomes minus infinity. This distinction is one that we will need later on. Okay, so that's already very nice. We have seen that if you express your primal problem in the standard form, that you can then always lower bound it, the optimum value by using this dual function. And we have seen, moreover, that this dual is a strictly concave function. And it is now natural to ask for the tightest possible value. So how good can our bound become? So we've seen that we have a lower bound, and now we want to know what is the tightest lower bound that we can achieve. And our tightest lower bound, or the value that we can achieve, is going to be d star. D is for dual. So this is the optimal value of the dual problem. And to find it, we need to maximize over these dual variables. Still under the condition of lambda being non-negative, because only then can I guarantee that I do have a lower bound. And one can say that the problem is dual feasible for the dual taking values larger than minus infinity, always under the condition that lambda has to be non-negative. Well, and then we can ask for the optimal Lagrange multipliers or you can also call these the dual optimal variables, and this is given by the pair lambda star nu star, which maximizes your dual. So we had a function that was purely concave. We have a maximization, and the maximization of a concave function is the same as the minimization of a convex problem. So we can say that overall this is a convex problem. And again, I should stress it is a convex optimization problem. Even if the primal problem, the original problem, is not convex. Now, the price that we pay for this simplification is measured by the duality gap. Which is defined as the difference between the optimum value of my primal problem and the optimum value of the dual problem. And there are then two properties. There is weak duality, which always holds. We have already shown it. Is that the optimum value of the dual is always less than or equal to that of the primal. So this always holds as long as our problem is dual feasible, well, even if it's not dual feasible. This always holds. And then we have the much more rarefied property of strong duality, where it turns out that we did not simplify the problem, that it's really equivalent if we solve the primal or the dual. So in this case, our lower bound is tight. Okay, let's have a break here. After the break, I will look at the linear program as an example for this primal versus dual, and we'll then talk about the Karush-Kuhn-Tucker conditions before finally moving on to linear program in much more detail. If you want more examples, you will find plenty in the book of Boyd and Vandenberger, which is also available online. And let me say again, it is a very fine book. I want to give a single example here, namely a standard form linear program, which we will talk about later today. Here we minimize a cost C transpose X. So C is a vector of cost variables that is supplied. X are the variables that we want to optimize over, subject to in standard form we have the following constraints. So x is a vector, and if I'm writing then greater than or equal to, what I mean is that this should hold for every element of my vector. So to translate this into our formalism, I can say that we have inequality constraint functions fi of x. I wanted x to be larger than 0, so I can say that minus xi should be less than or equal to 0. I can then build the Lagrangian. My original objective was C transpose x plus the summation over all the Lagrange multipliers I can write as a inner product between these two vectors. So this term here was shorthand for the summation over I to n of lambda I minus xi. And I can now isolate the term that is independent of x, which is B transpose nu. And then everything that I need to multiply with x, so I have a C transpose here, and I have a minus lambda here, and I have a plus nu transpose A times x. And I can then go on to build the dual. By taking the infimum over my Lagrange multiplier of my Lagrangian, sorry. The first term was independent of x. Okay, now we have two possibilities. So either we have a special case where this this term here evaluates to 0, then the infimum is going to be, or my dual is going to be minus B transpose nu. It's only true if C transpose plus nu transpose A minus lambda transpose is 0. Otherwise, I get a minus infinity. Because I could take values lambda and nu that make all of this here arbitrarily, well, that give me, no matter if this is a positive or negative value, I could let this go to minus infinity by letting my x go to either plus or minus infinity, depending on the sign of this thing here in the parentheses. So this is uninteresting. The duality, or the weak duality, still holds, but it's only informative if my dual function takes on values larger than minus infinity. So the lower bound that I get is only meaningful on the one hand if lambda, that I always require in order for the whole thing to be a lower bound in the first place. So I require that lambda be non-negative. And here in addition I want C plus A transpose nu minus lambda, that should be 0. or I can, knowing that lambda should be larger than or equal to 0, I can also rewrite this as C plus A transpose nu should be larger than or equal to 0. And this allows me to express my dual linear program to find the tightest lower bound possible. I will maximize over minus B transpose nu. I have now these new dual variables, lambda and nu, and I want to make this value here as large as possible, subject to A transpose nu plus C being larger than or equal to 0. This is just what we saw here. So this is a dual linear program, and now we have an inequality here. This is called a dual linear program in the inequality form, whereas here we had a primal linear program that was in equality form. And that is not an important distinction. We will see in the next hour that you can translate standard form to inequality form and vice versa.
So by doing this, we get the minimum or primal or the maximum of the dual.
Yes.
And if we want to know the actual values of x, where the primal takes the minimum, how do we get there from the result here?
I think we can get it from the complementary slackness equations. Let me see if that is true. Yeah.
Random two variables are linked while the complementary slackness
Yeah.
equations are unique.
Yeah. So what we find is that in this particular example here, that ax minus b, and now its Lagrange multipliers are the nus. So nu transpose times that should be 0. And if we have found nu, so the dual solution, then we could now via this equation solve for x, the primal. But in this case, we have actually going to the dual in this case was no simplification, because you see this has the same hardness as that one here, and it is more a matter of which domain you find more convenient to work with. So, for example, you could have many but low-dimensional constraints here, or few but high-dimensional constraints in the dual, but the overall effort is the same. So if you really want the x, then you would simply solve the primal problem here. Okay, so the main point of this slide was that I wanted to show that this, normally you find recipes for how can a linear program be translated to its dual, inequality constraints become equality constraints and vice versa, but you can really do it step by using this